Welcome back, everybody. In this video, we're going to be taking a look at EIGRP load balancing. Now, EIGRP load balancing supports both equal cost and unequal cost load balancing. So what that means is unequal cost requires a feasible successor to be candidate for injection into the rib. So what actually ends up happening here is as long as there's a secondary route to a destination, if its feasible distance is higher than the feasible distance of another route, what will end up happening is the lower computed metric feasible distance, also known as the successor, will get injected in the routing table, and its backup path that has already been pre-calculated and EIGRP knows which path to send the traffic in, that's also referred to as the feasible successor. That route will stay in the neighbor table, or I'm sorry, in the topology table, until the successor route is no longer, the primary route is lost. Now, we can manipulate EIGRP in such a way to allow us to use both routes at the same time. So what we're going to do is we're going to take a look at this on our topology. Oops. Wrong. There we go. So we want to make sure that R7 can use any path to R8 it needs to reach R8's loopback. So go ahead and pull up our topology here, and we're going to go and do a show IP route. And we are using just one path to the 10.10.8.8 network, right? So we're going to go in here and do a show IP EIGRP topology table. And to get to the 10.10.8 network, we're using the path towards R6. But if we do show IP EIGRP topology all links, we should have two paths to get there. Let's see here. Oh, you know what? I bet you I know what the problem is. On R8, if we do a do you all, and if we do a do show run interface fast set at 0/0.89, that's what I thought. So let's go underneath the interface fast set at 0/0.89 and no summary. The problem that I believe we're running into back on 7, if we do, that's what I thought, is because of the fact that we were propagating the route in such a way. If we do a show IP route again, we should have, there we go. Yeah, because of the default route we were getting, it was skewing our results. So if we do a show IP EIGRP topology all links, we're going to have multiple paths to the same destination, which means the 10.10.8 network is available via both paths, and the 192.168 is available via just one direction. So what we need to do is we need to go in here, and so for the 10.10.8.8 network, show IP route for 10.10.8.8, we're going to use the path towards R6. Well, I wanted to leverage both links. So what I've got to do here is I've got to do some breakdown. I got to figure out what it is that I have to do to make both routes able to be injected into the routing table. So this is my feasible distance right here, 158,720. That is for the primary route. That is the route that is injected in the routing table. So we take the path towards, there's our 158,720. So we're taking the path towards R6. I have another path here via R9 with a feasible distance of 412,160. So I'm pretty good at math, so that's about a 3 to 1 split. We're going to go ahead and just take our good old-fashioned calculator here. Give me a moment to go pull that up. And in the calculator, we're going to go ahead and pull this in. We're going to say, we're going to divide 412,160, divide that by 158,720, and it's a 2.5. So it's about roughly 3 to 1. So what I need to do now is I need to make EIGRP on router 7 look at this route and say, I will accept any routes when you take this as the base computation. So this is your this is the value you use to multiply against with. So if you don't know what I'm talking about, let me go ahead and jump into global config. So in order for unequal cost load balancing to work, go into router EIGRP1. There is this capability known as variance. The variance is a multiplier. By default, it's a value of 1. If we do a do show IP protocols, if you look at the variance by default is 1. The reason why it's 1 is because we don't want to accidentally drop in routes if we don't want those routes to be in the routing table. So what we can do, using the variance command, we can use the variance, and based off of our calculation, which is 2.5, roughly 2.6, we can specify what by taking the feasible distance of the primary route, which is this guy right here, we can multiply that by 3, or use a variance of 3. And by using a variance of 3, we can say, okay, EIGRP will consider a route that is up to and equal to 3 times this value. So if we take the calculator and we do clear that, we type in 158,720 times 3 of 476,160. So as long as you have another route, in this particular case, the route towards R9, his feasible distance is 412,160. We look at this, we can accept up to a value, multiplying it by 3, of 476,160. So if I just type in the enter key here, what's going to end up happening now, if we type in do show IP EIGRP topology all links, it doesn't change anything here. But what it will do is show IP route. We will have 2 paths to this destination now, and they both got injected. Because what you're doing with the variance is you're saying, take this value right here, multiply it by 3, and that is the worst metric you will accept to put in the routing table. So now if I do a trace route to 10.10.8.8, the primary path in this case goes by R9. It should leverage both. 10.10.8.8. It's, okay, in this case here, it's doing some shear counting. Now what this means is when you're doing a traffic shear count, because of the fact that, and the reason why it's got to do a traffic shear count is it's going to send a number of packets this way and then a number of packets this way. So let's go ahead and take a look at exactly how R7 is going to forward this. There's a reason why I covered Cisco Express Forwarding, or Ceph, earlier in the course, so that when I did Ceph outputs, you guys would understand what you're looking at. Show IP Ceph for 10.10.8.8 internally. I want to look at and know exactly how Ceph process is going to forward the traffic. And as you can see, the very first packet that we send out is going to be towards R9. It's not a routing issue. And you might say, okay, well, how is it not a routing issue? The reason why it's not a routing issue is because of the fact that I have two routes to the same destination. EIGRP is going, based off of the difference in weight. You'll see that if we look at the hash bucket 0, there's 16 of them, so 0 through 15. Hash bucket 0, hash bucket 2, hash bucket 4, and hash bucket 6 allow us to go towards R9. The rest of the buckets, 1, 3, 5, 7 through 15, all use router 6. It's basically a 3-to-1 or 4-to-1 ratio. So if I did another trace to that destination, it's going to continue to use the same path. And notice how it does slightly take different paths now. Notice how it falls back and forth. As you keep doing this, doing the trace routes, this number will eventually change, and there it goes back. Now it flips back. What I did is I just went back by doing the traces. You'll notice that the traces change. I got 2 outputs here, and then I come down here and I want to use router 6, count down to 6 or 7, and then I fail back to R9. So it's going to continue to do this repetitively. and it's going to go back and forth. What it's doing is it literally is using every one of the Ceph hash buckets to forward the traffic with. So one of these we're going to be dual equal cost routing, and there we go. So now I'm going back towards R9. So what I just did is I just made two full runs. We do a show IP Ceph internal. We just made two full runs through the hash buckets, and it's going to continue to do this over and over and over again. So if you get what you might view as some inconsistent routing, it's not the routing process. Let me be very clear when it comes to load balancing or forwarding in general. All the routing table, show IP route for 10.10.8.8, all the routing table is doing is learning about routes from another router, running a best path algorithm on those routes, and injecting them into the routing table. It's a reachability capability. That's all you're doing. Once you've got the routes in the routing table, you download them into the FIB, the forwarding information base. If you do a show IP Ceph, this guy right here is your FIB. This is where the traffic actually gets forwarded. Because if we do a show IP route, if we were to do just the natural recursion here, the first step is, do we have a route to the destination? In this case, the first answer to the first question is yes. If we didn't, the traffic would simply get dropped. The second question is, what interface did you learn that route in on? We learned it on two routes, fast Ethernet 0/0.79 and .67. Now, because we learned on two different routes, there's a characteristic here that we need to keep at the back of our minds. One of the things that happened here is because EIGRP uses bandwidth and delay as its two K values to compute its best path selection, we need to take into consideration those values. Now, if you look at the traffic share count of 2 and 3 and 60, we're going to send the majority of our traffic towards R6. So what that means is, when the Ceph process looks at the forwarding aspect of things, it's going to look at that and say, okay, I have two exit interfaces. How do I forward the traffic? How Ceph forwards the traffic is based off of the hash bucket. The hash bucket determines how many times you send a particular packet out a given interface for a given destination. The routing table does not take care of that. The Ceph table does. The Ceph table is really important for you to understand. I can manipulate this in order to make it do some additional characteristics, like look at traffic flows and stuff like that. But at the end of the day, when I am done running the algorithm and I've injected the best routes, the RIB downloads the routes into the FIB. The FIB goes out, finds out the layer 2, the header of the next hop. It knows the outgoing interface. It builds your layer 2 header. So the layer 2 rewrite is already completed at this point. All I have to do is figure out what interface I'm going to send the traffic out of. In this particular case, I know where I'm going to send the traffic out. So based off of that information alone, we can deduce from there that using the hash buckets, you can determine what the forwarding is going to look like. I can get down into the nitty gritty and go, okay, well, it's going to use, R9, 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 and R9. It's going to use R9 4 separate times. 4 out of the 16 are going to be sent towards R9. The other 12 times it's going to be sent towards R6. So with that being said, that is the way we can look at the forwarding and understand the direction we're going in. So you might look at this, do a show IP route 10.10.8.8, and from a routing perspective, we should be load balancing. However, because of the fact it's unequal cost load balancing, that is not the case. We have to unequal cost load balance. That's why if we do a trace route to the destination, we take different paths on a regular basis. So now I'm taking the path towards R6. That's how you need to understand it. Again, it's not one of those things where we are going to be able to load balance the traffic. We can make this a little closer with the traffic share. It's not exactly straightforward, but you would have to actually come in here and manipulate the delay and the K values and some other stuff to get this closer to be 1-to-1. But the simple way to do this, if we were to look at this and say a show run interface fast Ethernet 0/0.67, and 79 is I have a delay of 1000 set on the interface of towards R9. So it's less desirable from a computed metric perspective. At the end of the day, all that matters to you and I is the fact that we know that we're going to be able to forward out both links. Just we're going to, what they refer to, we're going to favor the link towards R6 because of the fact that it's got a better metric. The Ceph table is smart enough to understand that. If we were to increase the delay on the link, that will further decrease the amount of traffic we send out that interface. And if we skew it too much, if we add too much delay, we're going to make the feasible distance too high to where it is no longer within the bounds of the variance command. So by tweaking one thing, you could have an adverse reaction on something else. So keep that in the back of your mind as well. At the end of the day, that's what really matters. As long as you understand how one configuration change can affect something else, that's what really comes down to it. You guys have been awesome. Thank you so much for hanging out with us, and we'll catch you in the next video.